Updated ATOM, Aldo's torsion oscillation model. The updated ATOM integrates the clarified pop-back mechanism, key ring overlaps, and concentric spheres of stabilization with the atomic resonance network, ARN hypothesis. It builds a more cohesive framework for understanding mass creation, neutrino flavor emergence, and resonance stabilization. Core principles of the updated ATOM. One center of the eternal field. The compression engine, the center of the eternal field, experiences infinite compression, storing energy in a pushback region. This pushback region periodically collapses under extreme pressure, creating a pop-back mechanism that unravels energy into 1D filaments, releases torsion oscillations that propagate outward. 2. Total 1D filaments and key ring overlaps. The pop-back releases torsion-driven 1D warp filaments that oscillate dynamically along their lengths. These filaments curve and overlap at their ends, forming key ring-like structures where nodes interact. The overlaps oscillate between configurations, e.g. 3-fold, 5-fold, 7-fold, corresponding to neutrino flavors. 3. Concentric spheres of stabilization. Torsion oscillations propagate outward, encountering concentric spheres where energy density decreases and phenomena stabilize. Inner sphere, high-energy torsion nodes form fundamental particles, e.g. neutrinos, quarks. Middle sphere, lower-energy oscillations stabilize composite particles, e.g. protons, neutrons. Outer sphere, weak oscillations support atomic nuclei and macroscopic phenomena, e.g. stars, galaxies. 4. Harmonic resonance networks. The torsion oscillations create resonance nodes in the eternal field. These nodes interact to form atomic resonance networks, virtual mass fields, oscillatory patterns that predefine the structure of stable particles. Mass condensation occurs when resonance nodes align harmonically. New and harmonized elements. 1. Pop-back mechanism as the source of torsion oscillations. Extreme pressure at the center causes the pushback region to collapse, releasing stored energy as a snapback event, the pop-back. The released energy forms 1D warp filaments with torsion oscillations. T equals A sin kx omega t. These filaments are dynamic, curving and overlapping to create key ring structures. 2. Key ring overlaps and neutrino flavor oscillations. The ends of the filaments oscillate, periodically overlapping in configurations. 3-fold overlap, stable, low-energy state. 5-fold overlap, intermediate state. High energy, less stable state. These overlaps correspond to neutrino flavors, which oscillate dynamically as the system evolves. P in UB equals left, sum n Cn square, Cm minus I delta En make T H bar right to 2. The transition probabilities reflect the energy differences between configurations. 3. Concentric spheres as stabilizing zones. The propagation of torsion oscillations creates concentric spheres of decreasing energy density. Each sphere represents a Goldilocks zone for specific phenomena. Inner sphere, tightly compressed torsion nodes stabilize into neutrinos and quarks. Middle sphere, energy dissipates, allowing composite particles to form. Outer sphere, further energy dissipation enables atoms and macroscopic structures. 4. Atomic resonance networks. The torsion oscillations form resonance nodes that interact across spheres, creating a network of harmonic interactions. Resonance stabilizes mass by aligning oscillations across nodes. Virtual mass fields guide the condensation of energy into stable particles. Emergence of phenomena in the updated ATOM. 1. Neutrino flavor oscillations. The inner sphere hosts the first mass evolution, where 1D filaments oscillate, curving into key ring overlaps. Neutrino flavors emerge from the periodic alignment and realignment of these overlaps. The flavors oscillate dynamically, driven by the tension and slack of the filaments. 2. Mass stabilization in concentric zones. As torsion oscillations propagate outward, inner zones. Energy density is high, supporting stable torsion nodes, e.g. neutrinos, quarks. Middle zones, energy density decreases, allowing composite particles, e.g. protons, neutrons, to stabilize. Outer zones, weak torsion oscillations support large-scale structures, e.g. atomic nuclei, galaxies. 3. Resonance and mass evolution. Resonance nodes form harmonic networks, allowing mass to evolve hierarchically. Neutrinos, quarks, protons, neutrons, atoms, molecules, stars. Mathematical synthesis.